Okay, so the population of deer in a wood is 600, like now, 600 deer. The population grows by 4.5% each year. Determine the total population size after 1 year, right? So go ahead and write that, try to figure that out on a piece of paper. Anyone watching from home, just press pause on the video and try it yourself, right? So the first thing I want everyone to do is, can we turn that percentage into a decimal? What is that as a decimal? 4.5% as a decimal is. You can all see my screen, right?
Mm-hmm.
All right. In fact, I should probably do like a split screen thing here.
4.5 is a decimal.
Yeah. 0.
0.045.
Lovely, 0.45. Okay. So how do we get the total population after 1 year?
Am I supposed to just speak out or no?
Sure, yeah.
Would we just multiply?
Yep. So by what? You can multiply by 0.045, right? That would be 4.5%, right? Mm-hmm. And that's 27 more deer. So we have 627 deer now at the end of year 1. Does that make sense?
Mm-hmm.
But I just I got 627 because I went 600 plus 27. But how can we get from 600 to 627 with just one operation? Like, how can we just go 600 times SWAT will give 627? Because that's going to help us get our formula. So that's the key. Can we figure that out? Take your time. 600. So everybody, take your time. 600 times SWAT will just give us 627 without having to add. Just multiply it by one number to get 627. And that's why I had that little. I made you all do that little quiz to try to practice this stuff, right? It's 1 point something, by the way. 1 point what?
1.045.
Good. Look at that. Does that make sense? Are we all clear on that? Is that okay, Elias?
Mm-hmm.
All right, cool. So now we have 627, and that's after the first year, right? Now we have to get. Why am I not writing this down? Sorry, can you see the paper?
Mm-hmm.
Sorry, I should be writing this down like everybody else. So when I went 600 and I times it by 1.045, I got 627 deer, and that was after the first year. So I'm just going to look at this year population. Right? Can you see that on paper? Yeah. All right. So what do we do for the second year? So take your time and try to figure out what it's going to be in the second year. And anyone watching from home, just press pause on the video and try it.
2.045, right?
So.
Or to the second power.
Right. So, but figure it out. Let's figure it out multiple ways, just so we all agree how many deer we should have after the second year, because it's supposed to be 4.5% of 627, right? And then like you add it on to 627. Does that make sense? It's supposed to be 4.5% of what it was last year. Does that make sense?
Yeah.
Right. So like we could go, that's 0.045 times 627. 0.045 times 627 to get around 28 deer, 28.215, although 0.215 of a deer is pretty gruesome, right? So let's just call that 28. So that's why I rounded to the whole number, because I'm talking about deer. Now, a lot of students ask me, well, how do you know what to round to? Well, I don't know, but at least don't tell me that there's such a thing as 0.215 deer, because that doesn't make sense, right? Anyway, so like So that would be 28 more deer in year 2, right? And what would we do with that 28? We would, to get how many deer in year 2? We'd add 28 to what?
27?
Right. Because we had 627 at the end of year 1, then we add 28, and that gives us 655 deer, right? Does that make sense?
Mhm.
So the cool thing though, and the whole trick is, and you were just mentioning it there, is how can we figure out 625 with just one operation rather than getting 4.5% of the last number and then adding it on? Because what if I wanted to figure out the deer population in 30 years time and it followed this same rate, or in 15 years time or whatever? Like, I can't be continually getting the percent of last year. So the trick is, how can we use our compound interest formula, like our exponential growth formula, to figure this out? So 627, right, was the first year, and we got that by multiplying by 1.045. We're all okay with that, right? So for the second year, do we all agree we could have done this? 627 times 1.045. Plug that in the calculator, see what it gives you. Is that going to work? And tell me why it works if it does. 627 times 1.045. Does that work?
Yeah.
Why does it work? Okay, can you see why that would work and why that would give you the population in year 2?
Because it's adding another year from
Right.
one.
Right. And when I multiply by the 1, it gives me, because it's kind of like this. It's just this. It's 627 times, like, it's just like 1 plus 0.045, right? And if I did the distributive property, that gives me 627. And that gives me the 4.5% of 627. That just gives me the 28. See? So that's going to, so this calculation will give it to me, right? So that's cool. So we've got this anyway. So that we all agree that this works for the second year. Does that make sense? Right? We all okay with 627 times 1.045?
Yes.
Okay, so we're clear on that. So that's clear. Okay, so but the cool thing is, hold on a second. 627. Look at that. We just decided, and we all wrote down, I hope you all wrote this down, that is 600 times 1.045, isn't it? So if I look at this, well, like 600 times 1.045 is going to give me what? What is that going to give me? What's that going to give me?
From the first year.
Yeah, it's going to give me
627.
627, right? It's going to,
Yeah.
oh, sorry, 627. But to get to the next year, I just need to multiply by 1.045 again. Now, that's the key. If you understand this, you've got the whole, all these problems will make sense if you can just understand this one line. This explains everything. Does this make sense that this is how we could get what it's going to be after the second year, right? In fact, let's do it. Let's plug in your calculator 600 times 1.045, right? Okay, which of course we all know that's just 627, isn't it?
Mm-hmm.
Right. So if we plug it in again and now multiply by 1.045 again, what do we get?
655.
Cool. So now we've got 655 with one operation. How awesome is that? We didn't have to get a percentage of the last year and add it on. We just did all this. All we were told is that we started, the starting point was 600 deer. And we were told that the growth rate was 4.5%. And that's all we needed. Because then when somebody said, hey, get me the amount for year 2, I'm just going to multiply by 2 of these suckers. And now I've got my answer. And I don't need to know what it was even in the first year. See? So what
I have
I
have a question.
Good.
My question is, so if you want to do it for the third year, would you just do 0? I mean,
yeah. Give it a shot. Do the third
so
year.
for the third year, I got 684.
Right. times 1.045, right? Times 1.045. That's for, this will give me 2 years. And you're saying just do another one. I get 3 years.
Yeah.
Cool. Yeah, let's do that. Plug it in the calculator and then times 1.045, enter. Oh, look at that, 684. I kind of rounded up, I guess, 684, 685. Either of those I will accept, right? Some students are like, well, it's deer, so I'm going to round down because they can't get 0.69 of a deer. Other students go, I'll just round it up. So either one I'm going to give as correct for the third year, right? So that is correct. That's the second year. So this is year 2, and we multiply by 2 of them. This is year 3, multiply by 3 of them. Are we understanding that this is actually a cool thing that will actually work?
Yeah, and then if you want to just take the shorter cut on the calculator, it's 600 times 1.045 to the power of 3.
Nice. If you want to take the shorter cut on the calculator, it's 600 times with an exponent, everybody. And anybody watching from home, press pause. How can I rewrite this with an exponent? The little number in the top right corner, like the squared or the cubed or power of 4. Pause in the video watching from home. How do you rewrite this with an exponent? 600 times 1.045 to the power of
3.
3. Holy moly. Oh, eureka. Because, hey, look, all I needed was the starting point, the 600, and the growth rate, the 4.5%. And just tell me what year you want. Ka-ching. Oh, look at the coincidence. Year 3, what exponent did we use? 3.
3.
So what do you think it's going to be for year 4?
4.
Right. 600 times 1.045 to the power of 4. All we got to do is figure out how to plug that in the calculator. All calculators are a little bit, your calculator is a little bit different. It's something like that, 600 star for multiply by, and then 1.045, and then power of the little hat 4. Everybody grab that calculator, stick it in, see what happens.
And if Patrick's asked for 50 years later, then we just go to the power of 50.
You're starting to teach this class. I might be out of a job here. All right.
And if you want to go to the power of K, you go to the power of K.
Yes. What about T?
T, you go to the power of T.
Power of T. Nice. Around 715, 716 deer, something like that, right? That's after 4 years. Are you with me?
I'm with you.
Lovely.
I'm with you.
You can all plug that in the calculator easy, right?
Yeah.
Beautiful. Now, but listen, it gets better. Like you said, okay, I mean, I asked more questions on that. Like I said, stuff like, okay, so get me 1, 2, 3 years. We've all done that. Get me 15 years, get me 20 years. So yeah, off you go now. 15 years, I want the population of deer, 20 years. And then for the formula, I want T years. So take your time. Anyone watching from home, press pause on the video and let's get these done, right? By the way, when I did that, did you all see half of the paper and half on the screen? Oh, whoops.
Right now I'm seeing the question 4. And now you covered up question 4.
Oh, what am I? I'm trying to, this ain't working very well.
It says find the formula for this exponent function using the formula to calculate.
So now you can see my paper and the question on Canvas at the same time, correct?
Okay.
Woo! Is that what you're seeing?
Yeah.
Oh, beautiful. Okay, so off you go. Year 15, year 20 formula. Everybody, let's do this.
I have a question.
Yes.
So when it says determine the total population size after 15 years, rounds to the nearest whole number, is question 4 relating to the question 3?
It's the same thing. Yeah, absolutely. I should say deer. I put deer here, but yeah, we're talking about the same thing.
Okay, I didn't know where that was coming from.
No problem. So 600 times 1.045 to the power of?
To the power of 15.
Perfect. And then 20 years would be just 600 times 1.045 to the power of?
20.
20.
Perfect. And so we'll just do both of those. We'll round them. I guess I'll do those now. Oh. Anyway, sorry. 600 times 1.045 to the power 15. Rounds to about that. And by the way, I'm just going to use my arrows. I'm going to grab that thing and press enter. And then all I have to do is use the arrows and change the 15 to 20. Like, so this arrow thing is useful, right?
All righty.
You don't have to type it all in again. Okay, so I got, you know, a 0.16. I rounded that down to 1161, and I got a 0.02, and I rounded that down to 1447. Did we all get that?
Mm-hmm.
So what formula have we got here? If it, in other words, if it was T years, what would you do?
If it were T years, we
Yep.
would do the same numbers, wouldn't we? The same formula,
Yeah,
but the power would just be T.
that's it. Done. And that's all I'm asking.
Wow. You
So
make it
was-
sound so simple.
Well, it is. You guys are doing so good. But now the only thing is this is a simplified version of events, and populations are not that simple. Life is not that simple. Here's what we just did. I'll just plug it in. I'm on Google Sheets now, and you can all just sit back and relax. Actually, even better. No, don't relax. Don't relax. If anyone wants to go to Desmos graphing calculator. Okay, watch this. You gave me the formula, which was y equals the population equals, okay, 600, right? Times 1.045 to the power of t, right? That's what you told me, right?
Mm-hmm.
Now I'm just going to graph that, and I'm going to go to my little graph settings, and the inputs, the x's, I should do. Okay, I'll try not to be. So instead of t, I'm using x. I hope that's not too confusing, but it's just the number of years. Are we okay with that? X is number of years. I hope that's not too confusing. Anyway, I'm just going to make my x-axis go from like -2 years, just so it shows up nicely, to we'll do 20 years, because that's what we did on our calculation. And the populations are around, you know, 1100, 1400. So I'm going to make my y go as far as 2000, just so that this shows up, right? And can you all see that graph? I'll just zoom out a bit. Can you see that graph now? So here is 0600. Tell me about that point there. What does that mean? Initially, 0 years, population of deer was 600. Remember that? And then we got 1627. Do you remember that point? After 1 year, the population was 627 deer. Agreed? And then we went up and up and up, and it goes up to 20 was about 1447. Remember that? Now, what?
That is not linear.
It is not linear. How do you know it's not linear?
Because the dots wouldn't go in a straight line.
Yeah, it's curved. So it's not linear because we've got a curve, right?
Yeah.
And if I zoom further out, if this population keeps going like that, it's going to go, it's going to shoot up, right? Now, the problem is our exponential model in the real world with populations doesn't work like that. Can anyone tell me why a deer population in a certain area, like a forest, or like, let's imagine an island or something, like why would deer population not just keep going up forever? Like what would keep population under control in deer? You know what I mean?
Well, hunters kill deer.
Hunters kill deer. Anything else?
Cars do hit deer sometimes.
Cars might hit deer. They could run out of stuff to eat, right? Like eventually they're eating so much.
There could be
grass.
scientists that are doing stuff to them to make them not reproduce.
Right. All sorts of reasons. But there's kind of like in real life, there's this carrying capacity. Does that make sense? There's only enough grass or leaves or whatever for so many deer. So at some point, the deer population levels off, if that makes sense. So the exponential growth, so this is the logistic growth function on the right here. This is real life stuff. This is really what happens. But part of this graph is exponential. Like, so when a population are kind of introduced to an area, they do shoot up. You know, it's like the more there are, the more babies there are. And then the next year, all those babies have more babies and they keep having more babies. And so that's exponential growth, kind of like what we just saw, right? What we did was the stuff on the left, the exponential growth, right? So that's real life, right? But the problem is eventually you're going to hit this carrying capacity where, the island, let's say there's deer in an island, they can only hold so many deer because they're going to run out of grass or trees or whatever. Or maybe there's coyotes that are eating them and they're keeping the population under control. So it usually tapers off after a while, if that makes sense. Is that okay?